Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome to the last session of today. So in this session, we plan to look at the cache systems and the coherence protocols which ensure that the right data is available to the processor uh, whenever it wishes to seek it from the main memory. So cache is inherently tied to memory subsystem, and we will first understand the aspects of memory subsystem and why there is a need to add a cache in the memory subsystem. So here is which tells there are typically we see in a computing system four types of memories, that is static RAM, dynamic RAM, flash memory, and a hard disk. So here is a comparison of uh, what do they come? I mean internally what is there inside each of these. Beginning with static RAM has a flip flop which can take two states, 1 or 0. Dynamic RAM has capacitor which can be charged or discharged. However, the in dynamic RAM, the refreshing at a periodic interval is required because the capacitor is not ideal, but it has some time constant, due to which it loses charge over a period of time. So it needs to be read and rewritten every 10 milliseconds or as specified by the manufacturer. Flash memory has a field effect transistor with floating gate. A hard disk, as you know, it has platters covered with magnetic medium. So static and dynamic RAMs are volatile, meaning if you take off the power, the data is lost. And if you see the speed wise, static RAMs are fastest. They are less than 10 nanoseconds access time. Uh, and dynamic RAMs are much slower. But the good thing about each one of them is that static RAMs are the fastest. Nobody can beat them. Dynamic RAMs have best density because the number of elements required to build one bit is much lesser than that of a static RAM. And the flash memories, they are slower, much slower. I mean, you cannot use them. It's good for thumb drive or something like that. And hard disks are definitely are used as a secondary storage medium. So in cache systems, we will use always static RAMs because we want speed. Speed is the primary criteria, though it consumes a lot of power and are not so dense. Whereas dynamic RAMs are used for main memory. So the reason being capacity and density. That's the reason. Though the speed is low and the volatility and followed by refresh is little bit of deterrent. But however, main memory is always made with the dynamic RAM, and these days you get what is called as synchronous dynamic RAMs or SDRAMs, so which are slightly faster in terms of transfer speed, but nobody can beat static RAM at speed. However, they consume a lot of power, they are costly, and their density is not so good. So you tend to use very little of that. Not as so main memory will always be made using dynamic RAM. So these two are of interest to us. So let us first understand the basics behind this memory access. So there are two operations that are performed on memory by the CPU, and the connection between them, as I said in the morning, there is an address bus which is unidirectional towards the memory. There is a data bus which is bidirectional, meaning memory can read or write, can be read or written by the CPU. And to indicate what operation is being performed, you have two dedicated signal. One is called as read and other is called as write. So those are the control signals. So at a time only one of them would be active. So when does read take place? So when a read takes place, when an instruction like load or move from memory to register, such an instruction is to be executed. So the load instruction enters the pipeline, okay, so which is fetched, then it is decoded. When it is decoded, it tells that it's a load instruction. So load instruction has an operand. What is the operand for load? It is the address, because load is going to read data from memory to the register or towards the CPU. Okay, so that address can be part of the instruction itself, or it could be in a register, but that is known where it is. So what does it do? It takes this address, puts it on the address bus, as we can see here. Just a minute. So it puts the address on the address bus, and at the same time it asserts the read signal, because the read operation is going to take place. The memory gets inside and looks at the address which has been given on the address bus. That is, that using decoding that address, it reaches a location in the memory and puts the data on the bus, and this data has to come within certain time, and then the CPU accepts that data. Okay. Write is where the instruction like store enters the pipeline. That has again got the address where it has to store, and it also tells the source, like right from this particular register to this particular location in the memory. So what does the CPU do? It takes the address from the instruction, it takes the data from the source, which typically would be a register, puts the address, puts the data, and asserts the write signal. What does the memory do? Memory decodes the address, reaches out to a location, and the data that comes on the data bus, it stores in that address. So this is how the read and write operations take place. And these are typically slow. One of the reasons being that it's a dynamic RAM, which it inherently is slower as compared to a static RAM. And then the operations are taking on the external bus, where the traversing through the bus, that itself, in a way, when the signals are going out of the CPU, the access times are much going to be slower than if the CPU is to access something on the chip itself, on the processor itself. So now coming to these memories, if you look at the programmer's view, they want unlimited amount of fast memory. Okay, in the sense that they don't want the hardware designers to put a limit on how much memory that they should use, because they can load a large amount of data or something like that, and they want that there should not be any such restriction. However, the realities are such that fast memory, SRAM, we saw is the fastest, but it is quite costly. So when we say costly, we are talking about cost per bit. Okay. So if you look at the cost per bit, then it comes the highest is the, in that sense, comes is the SRAM. But there is a silver lining in the fact that the programs that are running, which are inside this memory, they tend to follow what is called as principle of locality. Okay. So there are two principles of locality. One is called as temporal. So temporal refers to time, meaning that the same location in the memory is being accessed repeatedly, which means that at t equal to 0 it is accessed. The same location is likely to be accessed at t equal to 2, t equal to 4, etc. Can one of you unmute your mic and tell me where do in program we find such kind of pattern, or while executing a program, where do you find such pattern?
Hello?
Yeah, go ahead.
So in case of loops,
Yes. In case of loop, uh, the uh, the instructions that form the loop, they are repeatedly accessed. Any other location in the loop is repeatedly accessed. So this is in the program memory. The clue is data memory.
Sir,
The
if
loop
it is
function.
implementing a particular variable, then that would be
Yeah, like
different.
loop variable, the loop variable, or suppose you are adding numbers and that numbers are getting accumulated in one variable. So these are some of the possible candidates where the data memory is repeatedly accessed at the same location, and program memory, as we said, is definitely like the loop, the instructions that comprise of the loop, they are going to be repeatedly accessed. Spatial refers to space. That means if location n is accessed, at address n is accessed, then n plus 1, n plus 2, n plus 3 are going to be accessed. Okay. So this is true for like in case of loops. The if there is typically loops have got sequential flow till it reaches the end of the loop. So close by locations are accessed, and if they are arrays that are used in the program, then arrays you typically go with index, increasing index or something like that. So as a result, the locations which are close by are accessed soon. So what does the hardware do is that it makes use of this principle of locality to create an illusion. Remember, it's an illusion that the main memory is very large, and in between it inserts a small amount of fast memory. It has to be small because fast memory is costly, but this fast small memory, it is fast, that's fine, but the small memory creates an illusion that any data that the CPU wants, it tries to give it from the memory, sorry, the cache memory. The CPU will always generate, as I mentioned in the previous example, the CPU will always generate address which is going to the memory. Okay. But what the hardware designers have done, they are trying to create an illusion. How they are trying to create an illusion? Uh, I will the exact implementation I will show you in couple of slides from here. But now let us see why that illusion is required to be created. So if you go back in time historically, when the first PCs were available in 1981, the PC was launched, IBM PC was launched. If you notice here, uh, the green dots and the red dots, they uh, they typically uh, they typically like it's near 1. That means performance demanded by processor is met by the memory. Okay, so that is how that scale is 1, 10, 100, 1000. Okay, so if that is, they are overlapping with each other, meaning the CPU, I had mentioned to you earlier, 4.77 megahertz was the frequency of operation, and you have to also look at how many cycles were required to complete one operation. So you take all of that together. The memory parts then were something like having 150 to 180 nanoseconds, and the processor was comfortable even if the speeds were 200 nanoseconds. So that was the reality at that time. So one could build a system using dynamic RAM and the processor, and the memory speeds were matching the speeds demanded by the processor. But then that 4.77 megahertz become 8 megahertz later, then 16 megahertz for 286, 33 megahertz for 386. Then Pentium and all became 100 megahertz. So what happened was that the processors were scaling up their speeds very fast, which means they were requiring data to be served at a very short interval, whereas dynamic RAMs from 150 uh, nanosecond, they came down to maybe first 100, then 90, then they came, and today they are stabilized around 40 to 50 nanoseconds. Whereas the rate at which CPU wants is typically something like 10 to 15 nanosecond, but dynamic RAMs simply cannot give them. Why? Because memories have not become faster, the dynamic RAMs, but they have concentrated on higher capacity. So let's say when 8088 was introduced and the PC was made, the state of the art dynamic RAMs were 64 kilobits by 1. That's what the top of the line were in terms of the capacity. Now they have gone into MBs, tens and hundreds of MBs, but the speed has not scaled up that much. It has become maybe 1/3, but the requirement that the processor has gone, as we said, from megahertz they have gone to gigahertz. So that is where the problem comes in, that the memories are not able to keep up with the speed that the microprocessors demand for them to operate at full throttle. Okay, so this is the problem that we need to bridge this gap that is occurring between the expectation of the processor and the actual expectations actually met by the memory. So what is that we can do? We can do interleaving, meaning that you have two banks of memory. Okay, so the access starts on one bank of memory and it takes some time. And while the first bank is so odd and even means address 0 in one bank, address 1 in next bank, address 2 in one bank, that is the 0th bank, and address 3 in the first bank. Like this, you alternate between the two. By connecting, uh, this is achieved by using the appropriate chip select for these banks. So what is the advantage here? Advantage here is that if the sequential access is happening, a bank will be accessed for alternate cycles. So that means when the access happens for alternate cycles, the memory get twice the time to provide the uh, data. So thus that is one option. Okay, so this is used to overlap the memory delays. Thereby, the CPU gets an illusion that every time it is starting the access, the data is coming almost in time. So interleaving the memory is one option. Second option is wider memory paths. Okay. So because it cannot go faster, so the option is you in one cycle you get more data. That is today the DRAM modules are 128-bit wide, 256-bit wide, whereas the processor may be 32 or 64-bit data that they would want. Okay, so like I gave this example in the morning, Pentium is 32-bit CPU, whereas data path is 64. So two words are brought in one shot, so that because you cannot make them faster, we are making it wider. The last option which we are going to see now, because both these options 1 and 2, they really do not help because the gap is too high. So faster memory is used, which is called as cache, which is made out of SRAM, to give the frequently used data and code to the CPU. So these are stored in what is called as data cache and instruction cache. Okay. So now let us see how does this work. Okay, so this diagram shows you where is cache positioned. Okay, so if you look at Webster's dictionary, it says that cache, or in newspaper, or not newspaper, but on television, the reader says that a large cache of arm was found in from the terrorists, recovered from terrorists. So they went into jungle, and from there they got this, or they were stored in a cave or something. So they got it. The law enforcing agencies caught hold of it. So that is the original definition of cache, that it is a safe place for hiding or storing things. But in our case, where we are trying to understand a fast memory, it is something that sits between CPU and main memory. Now again, remember the slide that I began with, how the CPU accesses memory. So CPU, this is the address bus. So it puts the address on the address bus. This cache is what the hardware designer has put in. The CPU does not know about it. It thinks that the data access is going to go to main memory. But what does the cache? The cache is not just a memory, or this main memory is not just the main memory. It has got a controller associated with it. What is the role of the controller? The role of the controller, cache controller, is to intercept what is coming from the CPU. Then what does it do? The CPU generates an address. It expects the main memory to provide data very slowly. However, in between, the cache controller checks what is that the CPU needs. CPU needs a memory, wants to read data at location 100 is what it gathers. Then it goes inside the cache, checks whether 100 is data at address 100, is it present with me? The answer can be yes or no. If the answer is yes, we will see how it came there later. If the answer is yes, it will give the data to the CPU immediately because this cache memory is SRAM. So once it gives that data to the CPU, CPU feels, hey, that's quite surprising. I expected the main memory to give me data after 40 nanoseconds. How did I get it within 10 nanoseconds? But that is the whole thing. That's the illusion I was talking about. So the cache creates an illusion that the memory has suddenly become faster. Okay, so please remember that cache is small, main memory is large. So every access that the CPU generates may not result in data coming from the cache because it is small in size. And the reason for it being small in size we know, because it is very costly. Now coming back to the question that we asked, is it present in the cache? And we looked at the possibility of yes, but many a times the answer is going to be no. So what happens during that period? During that period, the data anyway the CPU is expecting on the main memory. So the controller, cache controller, when it finds that there is a miss, meaning the data that the CPU wants is not in the cache, it passes the address to the main memory and it asks the main memory not only to transfer that byte or that word that the CPU is wanting, but it transfers the entire block. Some books call it as a line, cache line. Okay? So this is an interchangeable word. So what is block? A block consists of 8 words, 16 words. Why are we doing that? Because we said that spatial locality. So currently the CPU is asking for location 100. There is a good chance that 101, 102 is going to be accessed by the CPU. So the CPU wants a word to read, a 32-bit word to read, but when the address is passed on to the main memory, the controller will request for 4 words or 8 words, depending upon how the cache is designed. Okay. So essentially, the owner of the data is main memory. There is no confusion about that. Cache contains a copy. This is very important. A copy of a portion, certain portions. Okay. And I told you what happens when the CPU begins the access. Okay. So it looks in the cache. Controller looks in the cache. If found there, it gives. Otherwise, goes to the main memory. While getting that byte, gets few more bytes, adjacent bytes, and gives the byte to the CPU and stores that byte in the cache because of temporal locality. CPU is going to ask for that location again. So this is the principle on which cache memory works. So now coming back to the memory, the CPU is looking for data from the memory. Okay, so we build what is called as a hierarchical memory. Okay, so how is this hierarchical memory built? A diagram will help us in understanding it. Inside the CPU, it is the ALU that wants the operands. And we saw in the morning that the first place where the operands are likely to be found for fastest speed is the register. So we can call it as level 0. So if it's found in the register, I mean, it's like a 1 cycle delay. Immediately next cycle, the data is presented to the ALU and the instruction is completed. If it's not found there, then there is a L1 cache. So this typically L1 cache is part of the CPU. Okay, on the same silicon, this cache is present. But if you notice here, there are this arrow says that as you go here, the size is smaller. Like registers could be 8 or 16, something like that. This L1 cache would be something like 16 kilobytes or 32 kilobytes, very low. Level 2 cache. Okay, if you go away from this, the size is more. So level 2 cache could be, let's say, 1 MB, but it is slower in access and it is cheaper too. So as you go towards the bottom of the pyramid, the size of the element increases, which is the becomes larger and larger, but the accesses are slower. Like main memory is slower than level 3 cache, hard disk is much slower than main memory, and the current local hard disk is not sufficient for you. You can add additional hard disk, which is at a remote on the server. So essentially, if you notice these arrows, what they tell is that the main memory holds the actual data. L3 has copies of data, the lines which were retrieved from the main memory. Some of these lines from cache 3 end up in level 2, and some of those end up in level 1. As far as CPU is concerned, it will expect, I mean, the cache subsystem will try to serve the data from level 1. If not found in level 1, level 2 has more number of lines than it, so it will look at level 2. If not found there, level 3, and finally main memory. Main memory is bound to have it unless it's a virtual memory. If it's a virtual memory, then some portions may be on the swap partition of the local hard disk. Okay. So this is how we build the memory hierarchy. So what you do is small amount of fast memory, which is costly, is put closer to the processor, and as you go away, it becomes slower and slower. So the aim of this memory hierarchy is to provide maximum memory which is cheapest, like hard disk. Provide access to the location that CPU wants to read or write, offered by the fastest, that is the SRAM. And you build a hierarchy, that is, as you go away, you have bigger and bigger size memory, which is cheaper per byte, but it is slower. But the data copying happens only between adjacent two levels, and if it's not found in there, the data is brought from further level. If L1 cache gives the data, then it is called as a hit. So hit rate is a measure of the performance. Like you should, a designer, a good design cache will give you more than 80 to 85% of hit rate. So most of the time it's a hit. That's how you save the time. Okay. And if it's a miss, then obviously data is brought in from the main memory. So what does that cache contain? That the block that we showed, what does it contain? What does this cache contain? It contains of three main parts. One is called as the directory store, meaning it's a label. See, again, I will repeat what I said earlier. The ownership of the data is with the main memory. Okay, so the main memory gives an address to that data. So the data is identified by the address. And when it is brought in the cache should indicate the source of that data that is in the cache. Means did it come from address 100, or it came from address 1000, or it came from address 8000? Where did it come from? Okay, so you have entries in the, I will show you a diagram. You have entries in the cache, and every per line you maintain whether that particular line, what is the original address from where it came, because CPU is going to generate that original address and matching has to take place with that original address. So directory is the first part. Second is the data. So we said that an address is put out to the cache. Okay, address is put out by the CPU. It ends up on the cache. Then it's not found there. The data is not found there. So it goes to the main memory. From main memory, data comes to the CPU. In between, that data is copied by the cache. And where does it go? It goes in the data section. Okay. So we have the data section, and it's like you can say that you are arranging a file in a cabinet. Then you put a file and you put a label also, so that from the glass window of that particular filing cabinet, you can clearly make out what file is present and what file is not present. Okay, so it's like that. The directory store is nothing but a tag that is given to the data line that comes from the cache to the main memory. From main memory to the cache. And finally, there is something called as a status. Okay. So one of the bits is called as valid bit. So whenever the data is read from the main memory and put in the cache, the valid bit is set. So it indicates that the data is valid. I will talk about non-coherency slightly later. At that time, I will talk about this dirty bit. So this is how it looks like. Between the processor and the main memory sits the cache. And this is the structure of the cache. 100. This is the tag. It means that this has location 100 and this has location 101. This has location 102, and let's say this is location 107 because there are 8 bytes per line of cache. Now, this concept that adjacent locations are stored, brought in and stored in one line. Okay, so you have put the address only for the first byte, but the address for the next one is implied because they are consecutive, and this is called as a cache line. So this line or holds a data block. So 580 is the tag for this line. That means this data originated at location 580, this at 581, 582, and so on. So I hope this concept is understood, that how the data is organized inside the cache memory. I already told you that the cache memory also has a controller. So it is the job of the controller to monitor what addresses are being generated by the CPU. It looks at those addresses. Once the address comes, let's say the CPU says, I want to read from 100, location 100 from the main memory. Okay. So this address appears on the address bus. It goes to the cache controller here. What does the cache controller do? Cache controller looks at the tags and it finds 100. Or if the, let's say to make matters little complicated, let us say the address generated is 102. Okay, so it comes here, then through its logic it finds that this is the tag for the line. So this is 100, means this is 101 and 102. So it knows that this data is available. So what does it do? It takes out this data and it sends it over the from the cache to the processor. So the processor generated an address. It wanted to read from the main memory. Cache controller intercepted it. Suppose the address that the CPU put was 600. Then obviously it's not here. This is 580 to 587, but 600 is not there. So what to do in that case? It will allow the cycle to go to the main memory, but while it comes back, and the cache controller will not only ask for that particular word, but it will also ask for whatever is the line size. Suppose line size is 8, then it will ask for the location beginning from what is required up to 8 more locations. So they all will be brought into the cache memory. So this is what the cache controller does. It is snooping the bus. It is checking what are the addresses inside the cache and the address generated by the CPU. Does it match with the cache? So remember that the presence of cache and the controller is transparent to the CPU and the software. Means CPU will start an access on the memory, and it will expect the data to come. Moment it comes, it proceeds. So it is like this, that you had an old car which could not cross speed of 60, but somebody comes and puts it a Ferrari engine into it. Everything is same. You suddenly find that the car is running at more than 100 kmph. You are pressing the throttle the same way, but suddenly the car is going very fast. So something of that sort happens here, that the CPU does not know that the cache is put, and it will simply generate the addresses, and cache will intercept those addresses and give the data. Okay, so there is a relationship between the main memory and the cache, and that relationship is called as mapping. Okay. So this is the algorithm that I mentioned to you, that address is generated by the CPU. What does the cache controller do? It will look at the processor address. Then the address that it puts here is matched with the tag. Okay. So it searches the cache to match the tag. If it's found in the cache, the copy of data is written from the cache. If it's not found in the cache, what does it do? It reads a complete line from the main memory. The data corresponding to one of the one among the what you got as line. So that data is given back to the processor, and the data is stored in the cache memory. Okay, so now the question that we have written is, which line in the main memory does one replace, because it may be already present there. So this is the answer. There is something called as mapping scheme. So I will not get into details of how mapping works, because that is pretty long to explain, but you can assume it like this, that these are the three ways in which the relationship between the main memory and the cache is established, because when the cache reads the data, it has to go at a specific place. Okay, because later it will be later it is going to be used to indicate that whether that particular data is found or not. So you have to the cache controller has to find this out very quickly. Remember that the CPU has started a cycle, and it is expecting the data as soon as possible. So this checking or searching has to be very fast, and for that certain methods are used, because once this mapping is done, after that it becomes where the data is to be searched, that also becomes indirectly possible. This is again a very detailed topic, how this mapping takes place. So I'm not going to cover it, or what is the meaning of set associative and fully set associative. What is important for us to know at this point is that these are the method by which the data movement between cache and the main memory takes place. So now the important problem that we are trying to address, because in a multiprocessor system, there is something called as a cache coherency problem. Okay. So now what is this cache coherency problem? I have said earlier too that the ownership of the data is with the main memory. So the data, typically what should happen is that data, whenever it is accessed, uh, particularly read is straightforward, in the sense that I explained you the algorithm, in the sense that whenever a read takes place, the cycle goes to the main memory, but before that it is trapped by the cache controller. And when the cache controller uh, checks that, when the cache controller uh, 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 traps that address, okay, at that time, when the cache controller traps that address, at that time it has to check whether that address is available with the cache. Okay, so now there are certain situations wherein the data in the cache is different from the data in the main memory. Okay, so this is called as stale data. Now, why this is a problem? And under what situation this is a problem? Let me try to explain. Okay, so let us say there is a variable I which is used as a loop index. So the program says that for I equal to 1 to 100, I plus plus do something. So now I is initialized to 1. Okay, now this I is in the memory and it is initialized to 1. Now the loop begins. So when the loop begins, one iteration takes place. So I has to be increased. I has to uh, you have to increment I. So now when this instruction comes into picture, because I is accessed, I is brought in the cache. Fair enough. I is read in the cache, I is given to the CPU, CPU takes I, uses that as an index, and then it increments I. After incrementing, it will store it back. So when it stores it back, that updated value is going to go in the cache because the variable is temporarily stored in the cache. Now the question that we have is original value of I when it was in the memory was 1. That was the value that was read. That was the value that was assigned to the loop variable. It said from I equal to 1 to 100. Now after that first iteration takes place, I is increased. So I becomes 2. So when this I becomes 2, it's obviously going to become 2 in the cache memory. Question is, it remains 1 in the main memory. This is what the problem that we are trying to address. Now take this forward. The loop completes. I becomes 100 in the cache. I remains 1 in the main memory. Now, is this of concern to us in the sense that if this remains like this, then will that affect the program? Now, if this I is discarded in the sense that the value of 100 that I has reached at the end of iteration is not used again, then this coherency or lack of coherency between the main memory and the cache will not affect your performance. But if subsequently in the program, if value of I is used, and at that time, if the main memory is accessed, then you are going to get stale data because the updated data is in the cache, making the data in the main memory stale. Okay. Now, if it's a single CPU system wherein only the CPU is the only entity that is accessing the main memory and the cache is sitting between the main memory and the CPU. In that case, there is no problem because whatever the CPU updated, if it accesses again, it will get it from the cache and the job will be solved. But if this a certain variable which was in the main memory has been taken into local cache by a CPU and updated it, and the main memory is stale, and this main memory is accessed by another processor in a multiprocessor system, we have a problem. Why? Because it remains 1 in the main memory. It has become 100 in the local cache of processor 1, but processor 2 also wanted to access that value of I, and what it gets is a stale value. And this cannot be allowed to happen because you introduced cache for improving performance. You introduced cache for better efficiency. But if that results in incorrect results being generated, then that is absolutely a big problem. So we cannot allow that to happen. So what is a solution to this? One solution to this is called as write through policy, meaning, as the name suggests, write through. What does it signify? Write into the cache as you were doing earlier, but don't leave it there. Write through the cache into the main memory. So when you write, when the I++ take place, when I++ takes place, then cache is obviously going to updated. The variable in the cache memory is going to be incremented. Same time, the variable in its location in the main memory is also going to be incremented. What does this ensure? It ensures that data in the main memory is not stale, never stale. But can you tell me what is the disadvantage of this policy?
Writing operation becomes costly.
Slower,
As it
yes,
is,
very good, correct. So you are getting no advantage. And take the situation where I is used and never I is incremented, and then they just left. Every time you are writing it in the main memory and losing precious time, because the CPU cannot proceed unless the memory says that job is done. So this has its own implication. So though it is safe, it is not performance optimized. Its performance for reads are good, but its performance for writes are extremely bad. Okay. So what happens is in that case is that there is a I will show you a diagram subsequently, which will help us in understanding this, like how this is handled. Okay. So now here we are looking at a multiprocessor system. So if you imagine that these three processors did not exist, if these three processors did not exist, and the CPU is this is the C is the cache, and the CPU is getting data from the main memory. So now that is not shared because these processors do not exist. So it's a simple memory. So a copy of the uh, data in the main memory is retained in the cache and used from here. And there is lack of coherency. They are not same. This is tolerable because nobody else is accessing this memory. But imagine a situation that you have a multiprocessor system, each processor having its own cache. Let's take a variable x, and that variable x is in the shared memory. Okay, so processor 1 reads it. Value of that variable is 20. So it comes here and it is maintained here as 20. Okay. Processor 2 also reads it. Okay. So it also gets it 20 and they are using it. They are just reading it using that variable, not updating it. Now CPU 1 is updating that variable. So that 20 becomes 21. Whereas it is 20 in processor 1's cache, it is 20 in the processor 2's cache. I'm sorry, in the main memory. Now processor 3 wants to read that variable. What should it get? It should get 21, but 21 is here. 21 is not here. This is a problem. This is a problem that the cache coherency protocols try to address. Okay. So now one of the things that that one of the solution to this is, as we said here, is the write through policy. Okay, so one of the things is that the CPU has updated, made this 20 as 21. So it will also update the write through policy. It will update it to the shared memory. But as I mentioned just now, it is still 20 here. So how is that handled? That is handled by what is called as snooping. Okay. So what happens is that in this case, this cache controller is snooping the bus. Snooping is what? Sitting and watching, like a drone. A drone is snooping on a road and checking how the traffic is. So that is snooping. So whenever CPU makes variable x as 21 here, to maintain coherency, it will make 21 here. And this transaction, that address is x, value is 21, is monitored by the cache controller here. So don't go by this position that it is not connected to the bus, but assume this as an integral one element. So the cache controller here watches, which is watching, sees X as the address. That is here. There is a match, and the value is also going with it. So it grabs that transaction, updates the local value of the cache. This is one solution. So whenever, now there are various solutions. So this is one simple thing that I explained to you. One has to look in totality. What is the how the entirety of the solution is going to be achieved. So this I tried to explain you what is the snooping and why it is required. Okay, so that is one method. But again, because it needs to use write through policy, then the writes are slower. Okay, so this is one aspect of it. Now let us try and look at some slightly bigger picture. So the problem of this cache coherency comes in because each processor has a private cache. Remember, these are private caches, whereas the origin of the variables is in the shared memory. You can assume single level caches. Why I mentioned single level is in the diagram that I showed you earlier. I am talking about level 1, level 2, level 3. So we will ignore these levels. We will just say that there is a CPU and level 1 cache, which is private, multiple such CPUs, all sharing the main memory. Okay, so that is the situation we are trying to look at. Okay, so coming back here. So processor does an update on a location in X. That's what I mentioned. Other caches may hold copies of X. I said that it becomes 21 for processor 1, but CPU 1, but CPU 2 has the old value. So this copies will be out of date, because what can the processor which is updating do? It can update the main memory also, but that alone is not enough. So we maintain certain attributes for every cache line. So the granularity is on the cache line. That means this MESI, as it's called, MESI, will be the status bits that will be attached to every line. So there will be a MESI for this line, a MESI for this line, MESI for this line. So what is this MESI? Okay, it stands for modified, shared, exclusive, and invalid. So these are the attributes to the line. So let us see what is the interpretation of this attribute. Okay. So modified, what does it mean? Modified means that the cache line has been modified. The example that I gave you, CPU 1 updated X from 20 to 21. Okay. So we acknowledge the fact that it is different from the main memory. So main memory sometime, somewhere, I mean, either write through policy, immediately update it, but we said that that is not so efficient. So we may use some other policy, but we are acknowledging that the data, the line in this processor is modified. So we are keeping a track of that. Okay. But the good thing is that no other processor has it. No other processor has it in the cache. This processor, CPU 1, is the only processor which has its copy. So that is how it maintains it. So just modified means that it is the only cache, but it is modified. Now this is different. This modified is different from exclusive, because exclusive has the same connotation that it is the only cache copy. No other processor has it, but it is yet to be modified. Means just read has happened. So CPU 1 has read it, and the cache line is same as the main memory. So there is coherency. Okay, in this case there is no coherency because it is modified. Okay, and what is the similarity between modified and exclusive? The similarity is that no other processor has it. So that is one type of uh, attributes which tells whether it is exclusive or exclusive but modified. Okay, so they have to be, see, there is a bit for exclusive, there is a bit for modified. So you can have multiple combinations of these. Okay. The third bit stands for shared. So in case of shared, see, it is same as that. It is the contents of cache line are no different. They are exactly same as the main memory. But remember that copies exist in other caches. So two processors, at least two processors have read that line. I am not the only one who has read it. So any change that I make it will have to be communicated to the other processor which is holding it. That is the important message for this shared. Okay. And the last fourth bit is invalid. Invalid means the data in the cache line is not valid, meaning it will have to be read from the main memory. Now again, if you want to further understand this, we will have to draw a state diagram that what makes an exclusive bit exclusive memory modified, or how does a shared cache line become invalid. So there are state transition diagrams that you will find in books that describe this, but having a very short time for us does not give the liberty for me to explain that. There are use cases that are said that how does one go from one state to another, and the crux of this lies in two things. First thing is that whenever a processor is accessing a variable, it should get the latest copy. That is the first and foremost thing. You may say that I am repeating and making you sick, but please remember this. This will be useful to you in any algorithm that you design. Your performance improvement should not be you inserted cache, you had cache, private caches, and for every processor to improve the performance so that whenever the processor wants it, give it from the local cache. There should not be any contention. But this is the fallout of that, that the data that your processor has may not be the one that is the latest. So the cache design principles say that first thing, that any processor accesses any memory location, any variable, it should get the latest value. It should never get a stale value. Second principle is that how can you make that happen with the least performance penalty? Like I gave you an example, a safe way is write through. But we said that we got an answer that write throughs are slow, so no performance benefit while writing. But can you write it locally, but make sure that sometime anybody wants it, that is copied to that particular cache? That's another option. You make that fellow wait, say that, hey, don't proceed. Yours is not exclusive. I have the later copy. Please hold on. I will give you the data. So for situations where like that variable I, which was multiple times getting updated in the loop, and the updated value is available with only one processor that updated it, and somebody now wants it, what is the point in every time you update it, give it to other caches? That's inefficient. But can you make a foolproof method that whenever anybody wants, you make him wait and give him the copy that you have? So these are the design considerations that come into picture, which unfortunately is beyond the scope of our limited time discussion. But the whole purpose of making you aware of cache is that uh, uh, you have to, in case of HPC, or for that matter any algorithm that you write, if you can write an algorithms such that most of the time the data that you get are served from the memory, from the cache memory, instead of always going to the main memory, that will make your programs run efficiently. And there are techniques, documented techniques, known techniques, how to write a cache efficient algorithm, how to make sure that the data you have cached is the one you use repeatedly, before trying to see. If you try to spread your access very wide in the memory, then your cache is not going to be of help. If your algorithm is such that it is repeatedly working on a small section of the main memory, which can be held in the cache, then your algorithm is going to run very fast. But if you are, let's say, if you write an algorithm which, suppose your memory is 1 GB and your cache is 1 MB, and if you write an algorithm that it reads sequentially from location number 0 to location number 1 GB minus 1, then you are not going to get any advantage of the cache, because every time is going to be a fresh read from the memory. So point I'm trying to make it, uh, when you know how the cache memory is organized, you can write an algorithm that works in sync with the cache uh, design that has been done for a given processor. Or you can also write an algorithm that is counterproductive, just to prove that your cache doesn't work. And remember that uh, uh, if there is a penalty when there is a cache miss, you have to get it from the main memory, put it in the cache, and give it to the CPU. So sometimes if your cache hit rate falls below a certain number, for argument's sake, let it say 70. If the hit rate is less than 70, let's say, then you are better off not having cache. Directly allow every access to the main memory. So you have to retain, your design should be such that it is giving you 80 to 85% or 90, whatever best you can achieve, to make the presence of cache itself worthwhile. Otherwise, you can say that I don't need cache because my design is such that I am getting 50% times only I am getting hits, because of which the penalty that I pay for the 50% of the time negates or is much more than the performance that I gain in the 50% of the time. So this is, I mean, it's a very vast and complicated topic. I am trying to trivialize it to you. So that's all I have for today. So any questions about today's session, or particularly what we discussed about memory and cache?
Hello, sir.
Yes, go ahead.
Sir, I have some 2-3 doubts about this.
Yeah, please go ahead.
One is we have word transfer between CPU and cache, and there is block transfer or line transfer between cache and main memory.
Perfect.
Yeah. So my doubt is, suppose if the block consists of, let us say, 4 words.
Correct.
So and let us say cache access time is 1 cycle, and
Yeah.
main memory access time is, let us say, 100 cycles.
Right.
So whenever the CPU is accessing a particular word, and if
Right.
it is not found in the cache, so it will be brought from main memory to cache. So
Right.
will it require 100 cycles, or will it require 400 cycles, because it is bringing 4 words into the
Right. Right. So width of the main memory to cache is as wide as the block size or the line size.
Okay, so it will take only 100 clock cycles to bring it from main memory
I
to
mean,
cache.
again, since I have not described to you how that main memory behaves, see what happens is that's where that synchronous DRAM comes into picture. So
Okay, sir.
synchronous DRAMs internally, I mean, I will not go into details, but internally they hold a little bit of SRAM in a way, the
Okay,
synchronous DRAM, and they are able to operate because SRAMs are, and internally they contain banks of DRAMs, the capacitor based, the slower ones. But
okay,
what is presented at the bus of the SDRAM is actually what is called as SR latches. But I will not to
okay, sir.
complicate the matter, but assume that it is like an SRAM. So they
Okay,
work very fast. So if access and if, as you rightly said, if I were to access only one location in that SDRAM, it would have taken 100 cycles. But if you want to access 4 words, it will not be 100, but possibly it may be 150 or something like that,
okay,
because it is much faster, but it may not happen in one clock, one transfer, but it will do in a slightly different manner because
okay,
of
okay.
the clock signal present. Okay, so you have a point. Your question is very good. Go
Uh,
ahead. Next one.
Sir, and then further, that data will be transferred from the cache memory to the CPU.
Yes.
So, I mean, the total time will be time to access from main memory to cache plus from cache to CPU, or
Perfect. Yes, you are right. You will have to add 100 plus something,
okay. So, for example, 100 plus 1 clock cycle, like that.
or whatever, something like whatever that time is.
cache.
So because yeah, so
Number
though
of
there
cycles.
are, yeah, go
Number of
ahead.
cycles to access main memory plus number of cycles to access cache memory.
Yeah, so there is, I mean, it is not that particularly as a, I mean, that kind of mathematics, but it will be more than that time
Okay.
taken to access that main memory, we can
Okay.
say. Okay, so since you used one cycle, that comes into picture, but actually it may not be one cycle, it could be slightly more than that.
Okay.
So something in between that, suppose let's assume that it is 4 cycle from CPU to cache and 100 cycle from CPU to main memory. So it
Okay.
will be a number between, let's say, 2 or 3, but less than, I mean, somewhere around that, something,
Okay.
because some actions may happen parallelly.
Some
And
overhead
depending
will
on,
be there.
yeah, so
Okay. Yes, sir. Thank you, sir.
next
Hello,
question.
sir.
Yeah,
Sir, I'm having an application which is caching the data coming from the server, that is from
right,
a remote server, and I'm
Ah.
storing that in shared preferences or maybe in local one map, a simple map. Okay. So basically, my problem is that the data is updating at the server by any some other user. Okay,
Right,
and I'm not able to listen to that data. Okay,
right,
so I want to update it. So one solution may be just after some 3 to 5 seconds, just go to server and check the data is updated or not. If updated, then fetch it and then again store it. So basically, I want if there is something algorithm which I can use for this task to make it efficient, because updating or getting the data for every 5 seconds is not going to be a efficient solution for that. So is there
right.
any efficient solution that I can implement out there?
Okay, so first thing is that you should know, I mean, to improve this. So what you have indicated is a brute force, that just go every 3 seconds and check what is it, and which just get that data, so that anytime your process needs the data from the local buffer, it will always get it, because you are ensuring that the latest data is always brought in, irrespective of whether you want it or not. But this is
Yes.
putting a lot of pressure on the bandwidth, because many a times you are getting the data which is anyway getting overwritten after 3 seconds, because you are not using it. Suppose, I mean, take a situation that at t equal to 0, you access the data from the buffer, your program access the data from the buffer, and next time it is going to happen at t equal to 10, but at t equal to 2, 3, 4, 5, 6, 7, you kept bringing the data which was not used, right? So
Yes.
that is a disadvantage of the scheme that you have indicated. So now, next, first and foremost thing that you need to look at in this situation is that you mentioned that on the server somebody is updating the data. So the first question is, whatever the data that is being updated there, uh, all of that, is it of interest to you, or only part of it is of interest to you? That is first thing that you have to see, because you should get only, there are two things, two important things. I mean, I will try to put it in a very simple manner, but things are not as simple as that. You should get the data, which only that data that you need. Okay, that is the first.
Yes.
That is the first thing. Second important thing, which was brought out in the example that we took, is that you should get that data just before you need it. So that is the second thing. If both of these things you are able to crack, then your bandwidth requirement will be minimal. Okay, because you are getting only that you want. And second thing is, you are getting it just before you want, because as a result, those redundant fetches which happened, which were anyway overwritten in your local memory, they are not going to then that they will be saved. So now the trick lies in figuring this out. So now there could be for the first thing, that is the data of your interest. If that is the case, then there has to be some communication between a process on the server side and your machine,
Yes.
that what is the data of your interest. Okay, and that is one way of doing it. Second thing is, the other process has to, I mean, the server has to tell whether that data of your interest, if it got changed. That is the first thing it can
Yes.
communicate. Only then you should go and get it. Then the next step is little tricky, as to you cannot anticipate when you will need it. And as a result, you get to know, I mean, your process, the fetching process gets to know only when there is an access. And in that case, what happens is you have to keep the process which is wanting the data in wait, go and get the data, which is again inefficient. And that's the reason why you have chosen that I want this process which is seeking the data not to suffer for time penalty. That's why
Yes.
you are doing redundant fetches. Okay,
Fetches.
so that is the tricky part of it, and that is
Yes.
where
So no, not like that actually, sir. I haven't done that. It was just one solution that came into my mind. But how actually I have done is that at server, one flag is there and it
huh,
is getting set and it is getting read by the application. That there is one connection between them. And
right.
whenever the data of my interest is getting updated at the server, I'm
Yeah,
throwing one message to the application that this data is updated and please
right.
update your cache.
Correct.
So this is how I'm trying to achieve it. I haven't
Right.
achieved
So
it,
this
but
is
I'm trying
safe.
to
This
achieve.
is safe in the sense that you are not doing redundant reads when the data is not updated. That part is saved, but you are still doing redundant updates even when you have not used the data. You are not interested in using the data at the process. However, to prevent the process from waiting for data update, this is a solution that you have chosen. So it is safe and maybe it is taking a middle path somewhere.
Yes, sir.
Okay, good. Next question, please.
Hello, sir.
Yes, go ahead.
Sir, can I ask one more question, sir?
Yeah, yeah, yeah. Please, please.
Sir, suppose if we have a single processor system,
Yeah,
in that case, will this cache coherency be a problem? I mean, for example, if the same processor modifies it, but at some point of time, it may have to write it to main memory or means I
right.
don't have multiple processors. I have only a single processor. Then which can be the best write policy that can be
Yeah.
used?
So, correct. So, what do they do? What they do in such cases is that actually there are two issues. One is that there is another processor or another master which is reading the main memory. If that is the case, then that thing we described.
Yes, sir.
Now,
Yes.
in this thing that you are telling, there is only one processor,
Yes.
and
Yes.
the data is in that case. What they do is they will never use a write-through policy. Doesn't make sense because
Okay. Sir.
nobody else is going to use the main memory. So there is
Okay. Sir.
no way that anybody else is going to get the wrong data. There is only one master, that is your CPU, which will always get the right data because it's there in the cache.
Yes. Sir.
However, there is a coherency is not there. Now this problem, this is so what they do is in this case they maintain a bit per line which is called as dirty bit. Okay,
Okay. Okay.
so
Sir.
which means that the data in the cache is fresh, but the data in the main memory is stale. So that
Okay.
is the word they use. Now where does it come into picture? Why is it required? It is required in the following situation. I have already mentioned to you that cache is small in size, main memory is big. I have not explained to you the mapping scheme, but multiple locations in the main memory map to a same location in the
Yes. Sir.
cache,
Yes. Sir.
right?
Yes. Sir.
So if the CPU generates an address which is to be brought in, and the where it is to be brought in the cache, that line is dirty, right?
Okay. Sir.
Because it has been updated in the cache. We are following a write back policy. We are not following a write through policy. As
Okay.
a result, the data in the cache is updated. It is not in the main memory, and you don't want to override the data in the cache with a new line unless you
Okay.
vacate the
Okay.
dirty line. So dirty line helps us in maintaining. So that access is slightly slower because you cannot simply bring it in. You have to first write the data from the cache into the main memory at a different location, because multiple location x dash, x double dash, all of them are mapping to x in the cache. So
Okay.
x dash is going to come in, but the data due to holding is for x double dash. So what you do is write the cache from x to x double dash, then get the data from x dash to x in the cache.
Okay. So that means write back would be the best one. And whenever we want to replace that particular location cache memory, that time writing will be performed to main memory.
Exactly. And it
Okay.
has to be dirty. If
Yeah.
it
Yeah.
brought
Yeah.
in and
Yeah.
only
Yes.
read happened, simply
Yes.
overwrite it.
Yeah.
Don't
Yeah.
worry.
Yes. Okay. Thank you, sir. Thank you very much, sir.
Yeah, yeah, no problem.
So
Mine.
actually, these are the doubts I was having. So it was very nice that you cleared this.
No, absolutely. And my email address is there. I think all of you have it in the communication that was sent which told you that you are from the sysadmin indicating that what are your uh, which said that that text of that email said that your individual emails have been created, IDs have been created, and you received another mail. In the CC, my address is there.
Okay,
ashish@cdac.in. Okay. So
okay.
just give me a reference. I may not know all your names. Just say that
Yes.
you attended the summer school, and I will know what all you know and what all we discussed.
Yes, sir. Thank you, sir.
Next question, please.
Adi, you can unmute yourself and ask the question. You are waiting from a long time.
Yeah, can you hear me?
Some background
Yes.
noise. So yeah, now
I think
please try.
great. So my question was, it's a bit more separate from this. So obviously we have cache coherence problems in multiprocessor systems, but isn't this the exact same problem in parallel computing when you have HPC clusters? So in HPC cluster, if I distribute my application across different nodes and there is a there's a coherence problem, how is it solved in that case? Because in that case, I have the the network latency also coming in, right? So how do you maintain coherence in HPC as compared? Like, what is the difference between coherence in multiprocessor systems versus in HPC systems?
Okay, so it is. I mean, the basic problem is same in the sense that you have a copy of data at multiple locations, and they are. I mean, in this case, it is at a maybe a nanosecond level. There, it will become something like microsecond or millisecond level. So one of the solutions that you have is you design your the ideal situation is you design an algorithm such that the when you have distributed the data to multiple nodes in a cluster, then there is no overlap of data. That is first way of doing it. But however, having said that, there are some boundary value problems, matrix multiplication like problems, wherein some of the data needs to be shared. Okay, and there is no escape from that. And there are Preeti would be telling you about introducing you to MPI, that is message passing interface, which is a framework, library based framework, wherein one can at that level, at the level of the programming, at the programming framework level itself, you can define which data is going to be having such attribute. And as I said, your design of the algorithm should be such that you should minimize such kind of shared data. But at the same time, there are some situations where you just can't avoid it because the algorithm is the need of the algorithm and you can't skip it. So in that case, of course, there is a penalty that you pay in terms of time. But I mean, you don't have to micromanage it. It is done by the framework. And there are other things also, like she will tell you primitives like broadcast is there, wherein everybody gets that. Of course, broadcast is the most time consuming thing, but that is the way it is. I mean, something which cannot be cured has to be endured, but you have to see how the pain can be reduced. That's it.
Yeah, that makes sense.
Yeah.
There was one more question, and that was about, so I think I don't think that we talked about prefetchers in this, but
Prefetchers at what level?
cache level.
Yeah,
Yeah.
so
So
yeah, go ahead.
no, my question is it's a bit different. The question is that, so I think in one of your earlier courses you told that sorry, we turn off hyperthreading for HPC systems, right? Now, in my personal learnings, I've also found out that we turn off prefetchers for high performance computing as well as for enterprise systems. Now, why is that the case? I do not fully understand why prefetchers are unable to contribute to improved cache performance for these kind of high intensity workloads.
Actually, that will I think that will depend upon what is the pattern of data access. Okay, so I think it has to, but what I will do is I will just go through rather than giving an incomplete answer, which I myself is not convinced, and I have a chance to interact with you on next Monday. So let me just go through this and I will give you an answer. Though I have a clue about why that should be happening, but I'm not 100% sure, which I don't want to take a risk.
No, please, it's it's not a risk. I mean, I'm just interested in
No,
knowing your
no,
perspective.
no, the see, point I was trying to make was I would like to give a comprehensive answer rather than a short answer. The short answer, which I'm 100% sure is that, I mean, which is possibility. That's what I'm saying. It may not be, there may be more possibilities that may exist. One of the possibilities about the fact that it depends upon the data pattern. So prefetchers assume that some things, some pattern that is going to happen. But if the pattern doesn't, what the prefetcher feels that pattern is not going, that's the, in that pattern, if the data is not going to be accessed, then it can be counterproductive. And to avoid that, because, and other thing is that that portion of what the, whether it has to be prefetched or something like that. So like that control should be with the programmer rather than the lower level CPU who may go wrong. And if he goes wrong, I mean, if it goes wrong, then the penalty to be paid is, I mean, that the upper layer cannot avoid. I mean, this is what I feel. But I mean, this is my, as I said, some part of guess and some part of what I know for sure. So that's why I will definitely, but it's a good question. That's why I want to visit it and answer it next time.
Thank you. Thank you very much. I'm really grateful to you for your advice. There's one last question. Yeah, so again, it's not really, it's a much more advanced question, but have you seen instances of load value prediction implemented in commercial grid systems in HPC or in enterprise or load value prediction? Because obviously the main memory wall has been with us for decades now. So any instances of load value prediction that you've seen?
No, I don't think I can. I mean, I have come across that, and not. I mean, more of. I mean, the reason for it is because that is not really my field of expertise. That's the reason it. I might not have come across it, but I will again look for that if at all I can find some references. I will definitely try and see. But that's not my. I mean, I can't claim to be knowing that field of information, and that's the reason why I cannot answer your question.